Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the distributed web crawler, the system that powers search engines like Google, Bing, Yahoo, and Baidu. We'll cover the URL frontier, politeness, deduplication, DNS caching, robots.txt, and the low-level design needed to crawl billions of pages. Whether you're preparing for a senior engineering interview or building search infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the distributed web crawler, the backbone of every search engine on the internet. If you have ever wondered how Google, Bing, Yahoo, and Baidu discover, fetch, and index billions of web pages every day while staying polite, fast, and fault-tolerant, this video is for you. We'll walk through the functional requirements, non-functional requirements, high-level architecture, end-to-end crawling flow, core models and algorithms, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building large-scale search infrastructure, let's get into it. Here is the core problem. The web is enormous and constantly changing. There are billions of pages, millions of new pages every day, and existing pages update at unpredictable rates. A single crawler cannot possibly fetch the entire web, stay fresh, and handle the immense DNS, bandwidth, and storage load. Worse, naive crawling wastes resources by fetching the same page repeatedly, ignoring robots.txt rules, hammering small websites, and failing to recover from broken servers or network partitions. The business needs a distributed web crawler that can scale horizontally, deduplicate URLs, respect politeness, cache DNS lookups, and prioritize the most important pages while keeping storage and compute costs under control. Let's walk through the functional requirements. First, the crawler must accept seed URLs and discover new URLs by parsing links, sitemaps, and redirects from fetched pages. Second, it must fetch raw web content over HTTP and HTTPS, handle headers, cookies, compression, and common status codes. Third, it must deduplicate URLs at scale using a Bloom filter or a persistent scene URL store, so the same page is not crawled many times. Fourth, it must parse and respect robots.txt rules and meta tags to stay polite and avoid restricted paths. Fifth, it must prioritize the crawl using signals like PageRank, recency, and change frequency so high-value pages are crawled more often. Sixth, it must extract and store content and metadata for downstream indexing, analytics, and ranking. Seventh, it must support recrawling and freshness policies so stale pages are updated without wasting resources on unchanged pages. Now the non-functional requirements. The crawler must be massively scalable, distributing work across thousands of nodes and crawling many pages per second. It must be polite, obeying crawl rate limits and robots.txt, so it does not overwhelm small websites. It must be fault-tolerant, recovering from node failures, network timeouts, DNS errors, and malformed pages without losing progress. It must be efficient, minimizing bandwidth, storage, and compute through compression, incremental updates, and deduplication. Latency matters for the freshest content, especially news and social sites. The system must be consistent enough that indexed content reflects reality, though some eventual consistency is acceptable. And it must be cost-effective because crawling the entire web is an expensive operation. Here is the high-level system architecture. On the left, seed URLs and sitemap feeds enter the URL frontier, which acts as a distributed priority queue. The scheduler pulls URLs, checks the DNS cache and robots.txt cache, and dispatches them to fetcher workers. The fetchers download pages and emit raw content to a content store and parse metadata to a parser. The parser extracts links, updates the scene URL set with a Bloom filter, and pushes newly discovered URLs back into the frontier. A prioritization service ranks URLs using signals like PageRank and change frequency. The indexer consumes parse content and builds the search index. A monitoring and analytics backend tracks crawl rate, success rates, politeness, and freshness. The key metrics to memorize cold. Crawl rate, usually pages per second or pages per day across the cluster. Freshness, the percentage of index pages that are recent relative to their change frequency. Coverage, the fraction of known URLs that have been successfully fetched. Duplicate rate, the percentage of URLs skipped because they were already seen or canonical. DNS resolution latency, the time to resolve a host name, often reduced by caching. Politeness delay, the minimum time between requests to the same domain. Failed fetch rate, the percentage of requests that return errors, timeout, or are blocked. Storage utilization, the total raw and compressed content volume. These metrics are what the business actually cares about. Let's trace the end-to-end crawling flow. A search engineer seeds the crawler with popular domains and sitemap URLs. The URL frontier hands a high-priority URL to a scheduler. The scheduler checks a cached DNS record and a cached robots.txt policy for the host. If the host is crawlable and the politeness window has passed, a fetcher worker downloads the page. The parser extracts the title, body, links, and metadata. New URLs are deduplicated against the Bloom filter and persisted to the seen URL store. High-quality content is written to the content store, and extracted links are scored and pushed back into the frontier. The indexer updates the search index, and the monitoring service records the outcome. This loop runs continuously across the entire cluster. The core models and algorithms. The URL frontier is a distributed priority queue that ranks URLs by importance, freshness, and politeness. The Bloom filter provides a memory-efficient probabilistic deduplication layer, allowing the crawler to skip already seen URLs with tiny false positive rate. Consistent hashing distributes hosts to fetcher nodes, so the same node handles politeness and robots.txt for a given domain. A DNS cache avoids repeated resolver lookups and reduces latency. The robots.txt parser caches policies and enforces crawl delay rules. Content fingerprinting using checksums or SIMHAsh detects near duplicate pages. PageRank and change frequency models guide recrawl priorities. The key trade-off is freshness versus load, because recrawling too often wastes resources and annoys webmasters. Now the low-level design deep dive. The URL frontier is implemented as a partition priority queue keyed by host and domain, with per-host queues and per-host politeness timestamps. Each URL is stored in a state table with a state machine, pending, in progress, completed, or failed. The fetcher workers run as stateless containers, pull work from the frontier, and respect per-host concurrency limits. After fetching, a parser pipeline extracts links and metadata, updates the deduplication store, and writes content to object storage. The scheduler handles retries with exponential backoff for transient failures and dead letter queues for persistent failures. A configuration service manages crawl rules, rate limits, and excluded domains. The system supports incremental recrawling by comparing content hashes before reindexing. Key takeaways for your interview. First, a distributed web crawler is a combination of a queue, a downloader, and a deduplication system, so emphasize the URL frontier, politeness, and fault tolerance. Second, always explain how to avoid duplicate work, using both Bloom filters and persistent seen URL stores. Third, politeness is non-negotiable. Discuss domain-level queues, crawl delay, and robots.txt caching. Fourth, the hardest design challenge is balancing freshness and load, so be ready to talk about prioritization, incremental updates, and recrawl policies. Fifth, mention real-world scale. Google, Bing, and Yahoo run massive fleets of crawlers with custom DNS, caching, and indexing pipelines. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the distributed web crawler. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the distributed web crawler. We covered the full picture, from seed URLs and the URL frontier through fetchers, parsers, Bloom filters, DNS caching, and the low-level design of the crawl state machine. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.